So with parametric equations, we want to describe motion in three-dimensional space. And to do that, we're going to describe any coordinate by three separate functions. So we're going to use three functions. Describe a point in space with three functions: x of t, y of t, and z of t, where t is the parameter. So rather than describing the coordinates in an equation relating all the coordinates together, or describing one coordinate as a function of other coordinates, we describe each of the three coordinates as a function of some outside parameter, something sitting outside of the location. And usually we interpret the parameter to be time. So at a given time, we evaluate x of t, y of t, and z of t, and that tells us the location of the point. So let's describe some common things. So if x, y, and z are all linear functions, then we will get a line. So let's suppose we want to describe the equation of a line containing the point, say x of t, x0, y0, and z0, and in the direction of some vector. Let's call back to our vectors. In the direction of some vector, a I plus b times y plus c times k hat. So we're going to use a vector to describe the direction, and we're going to say it contains the point x0, y0, z0. So a line will have a starting point and a direction, and we're going to do that in three-space parametric equations by just having the x be a linear function, the y is a linear function, and the z is a linear function. So our x of t will start off at x0 and have a slope of a, because that's the direction that we're going in the x. That's how things are changing in the x direction. Our y of t will start off at y0 and increase by b. And our z of t will start off at z0 and change by c. So we have linear functions in x, y, and z directions, and that's going to produce a line. None of this is very surprising. We want a line in three-dimensional space. We know that a line we pick a point to go through and a direction to go. That's all a line is: a point to start and a direction to go. And this goes all the way back to when we first started talking about lines with y equals mx plus b. Y equals mx plus b just says start off at b and go in the direction of m. That's all we're doing here. The reason that we want this framing device is that we want to write this in a vector form. What we want to start doing is describing this position with a vector. So we want to describe the position as a vector, because the vector will have three coordinates. Let me just write it down. So r of t is going to be a vector valued function. So vectors are a convenient way to gather up our three functions and separate them into our three different directions. the x direction, the y direction, and the z direction. This is why vectors are so great, because they summarize all this information, contain all three of these functions, and keep them separate. In an equation, all our variables are all kind of crammed together. And in a function, one coordinate, it has to be written as a function of the other coordinates. Sentences are very difficult today. I don't know what's going on. But the vector form separates all three of the three things that we want to separate. It separates the x, the y, and the z, and assigns it all in one vector valued function. So we can do that. We can summarize the equation of a line as a vector valued function by saying it goes through the point. Well, we could just write it down. So we'll just have each function, x naught and plus at, times I, plus y naught and bt times j, plus z naught plus ct times k. And then we can separate this out into this kind of form where we have a starting point and a direction to go. So our starting point is going to be x naught I forgot what I wanted to do with this. So we'll have an x naught. I just wanted to leave it at that. So what the vector does is separate out the I, the j, and the k components for the x coordinates, y coordinates, and z coordinates. And I think that's where I wanted to stop. So this is a position vector. Yesterday, we started talking about describing a path and wanting to describe what the derivative tells us. So if I just labeled something as position, you can probably guess what's coming up next. So if this is, say, a position at time t, if I make my vector a position vector at time t, so we plug in t, we get into x, y, and z, and we get the location of a point, then the derivative should tell us the velocity. So if our vector describes position, then our derivative should be the velocity at time t. Oops. So if r of t is a position vector, then the velocity vector is just going to be the derivative of r of t. So if r of t is just three functions all separated out, x of t, I, plus y of t, j, plus z of t times k, then our velocity, our derivative of this function, velocity, will point in the direction that we're headed. So x prime of t times I plus y prime times j plus z prime times k. Vectors separate out things neatly into these three components, or as many components as we need, and we can deal with them separately. How are things changing in the x direction? How are things changing in the y direction? How are things changing in the z direction? And more derivatives, the second derivative gives us the same thing we expect in single variable calculus. So if v of t is the velocity at time t, then v prime of t is the acceleration. So we have the same position, velocity, and acceleration, which is the second derivative. Which is all to say that it works exactly like we think it should work. Which is always our favorite thing to happen in math class, where things work just like we expect them to work. Any questions? All right. Let's pause here and then look for an example.